So welcome everyone to the Atto Fridays. This week's speaker is actually just around the corner for me because he's at UCL, and this is a bit surreal that he is talking here online, but we are welcoming him, and we are very pleased he accepted the invitation. So our speaker today is Professor Graham Worth. He is a professor of computational chemistry at University College London. He did his PhD at Oxford, developing free energy perturbation simulations for condensed phase thermodynamics. And then he went on to do postdoctoral work at the EMBL and Heidelberg University, where he started working on the MCTDH method for the quantum dynamic simulations of polyatomic molecules. He's now a lead developer of the quantic suite for quantum dynamics, which includes a range of algorithms to solve the time-dependent Schrödinger equation, including MCTDH, dynamics, and photo-excited processes. Present development work focuses on generating potential surfaces on the fly using direct dynamics. So we are really happy to have him here today. Welcome. And he's going to talk about photo-excited processes using grids and Gaussian Wavepackets. So welcome to the Atto Fridays. We are ready to start. The floor is yours.
Yeah. Thank you, Carla, and thank you, Lewis, for organising this and getting everyone together and getting the tech working. It all seems to work at the moment. Yeah, so what I wanted to talk about this afternoon to everyone is really to go over some of the methods that we've been developing for simulating the quantum dynamics of sort of molecular systems in principles. And we've got a range of methods that I will sort of come to. And while this won't be so much directly focused at Atto processes, these are all methods that can be used for Atto sort of chemistry processes, and I will show some examples of the sorts of things that we can do with them. Okay, so when we're sort of looking at light molecule interactions, because when we're trying to study these fundamental, very short time scale interactions and dynamics of molecules, we have to include the light, yes? And really, when we're doing this, there are the two, it's good to keep in mind, there are two limits that we commonly use in simulations. One is when we're doing a single frequency, so we're exciting a single eigenstate, yeah? So we've got an overlap between a ground state wave function and a single excited state wave function. And there you don't need to include a light pulse, you can just initiate your dynamics. And the other limit that we use is actually when we have a white light, and this is probably the most commonly used limit in photochemistry, because if we have white light, so all frequencies involved, this is equivalent to a delta pulse, because it's then a very narrow pulse in time. And this gives us a vertical excitation. So we have our ground state wave function that we excite, and we create a wave packet in the excited state. And again, you don't need to include the light pulse in this situation, because you just do a delta pulse excitation. So a vertical excitation of the pulse, and away you go, because that then includes all of the excitations of the eigenstates of the excited states, just using the sort of the Frank-Condon overlaps, the Condon principle. Okay, and these two limits relate to these sort of two pictures that we have in photochemistry and photophysics. So the single frequency, this relates very much to the photophysics limit, as we call it. So the Blonsky diagram, where we have all of the processes of excitation, absorption, fluorescence, intersystem crossing, where you go from a singlet to a triplet, or internal conversion from states of the same multiplicity, and so on. And that's really, you've started in one state and go somewhere else. Whereas the delta pulse, the white light limit, is when we have a wave packet moving over a potential energy surface. So it's a sort of quite a different picture for the dynamics we look at, which tends to be more the photochemistry picture, as we call it, because you see the photochemistry happening. And then the question, and this is really of relevance actually to Atto, is what about in between? If you have not just a very narrow, even though in Atto chemistry you obviously have very, very narrow pulses of light down at the Atto scale, you still, the shape of the pulse can become important. So what about in between? And then we have to explicitly include the pulse to see what the effect of the actual width and the frequencies in the pulse, if you have a shaped pulse in particular, on the dynamics of the system. Okay, so this means we need methods that can include a light pulse in our simulations. So to model what happens when a photon is absorbed, we need to solve the time-dependent Schrödinger equation. Okay, so we take our molecular wave function and propagate it in time using an appropriate Hamiltonian for our system and whatever it is we want to model. Okay, So what do we need? Well, we need a Hamiltonian, and this means we need potential energy surfaces. We need, obviously, the kinetic energy operator. I'm not going to go into any of this today as to where you get that from, but if you have the Hamiltonian for your system, you include the molecule light interaction. Yes, you need the transition dipoles and the coupling to the field and so on. Yeah, so, but once you've got that, you're ready to go. And then you need a method to propagate the initial wave packet, whatever that is. You're starting in an eigenstate, you include the light pulse or not, but then that's what I'll be talking more about today, the methods to propagate the wave packet. And then we have to think of a number of problems that have to be covered to be able to do this. Okay, so one is, well, we have coupling between the nuclear and electronic motion in the system. Yeah? So the common picture, in fact, this is implicitly put into the equation as I've written the TDSE here, is we have potential energy surfaces that are just a function of nuclear coordinates. And this is because we assume a Born-Oppenheimer type approximation, so that the electrons are following the nuclei, giving us the potential energy surfaces over which the nuclei move. But of course, you actually get coupling between the nuclei and electrons. Yeah? So it's not a clean separation at all times. And then you have to include these so-called non-adiabatic couplings that give us the means for going between the different electronic states that are defined by our sort of Born-Oppenheimer states. We then have a problem of, well, how do we actually fit a multidimensional potential function? Even worse if you have to fit the couplings to the light field. Yeah. And then you have the final problem, which is, well, how do you even solve the time-dependent Schroedinger equation? Because if you want to solve this equation directly, the effort required scales exponentially with the system size. So that really, in a sort of direct, straightforward way, limits us to very few particles. Okay, so if we're just looking at nuclei of the order of 3 or 4, that's straightforward to do, but any more costs a lot. Okay, so over the years, we've been developing, not just me or my group or wherever, but the sort of the field in general have been developing sort of a hierarchy of methods, different types of methods with different flavors to them. So just to sort of basically put up for me, the main categories of methods. At the bottom, we've got the accurate methods. These are what we call grid-based solutions. So we solve the time-dependent Schrodinger equation as directly and as accurately as possible. And these are methods like MCTDH. So Carla mentioned the multi-configurational time-dependent Hartree method that I've been developing now for quite a long time, and its multi-layer variation, it's called. And these are really great methods because they are variational equations that solve the time-dependent Schrodinger equation in principle numerically exactly. You can converge them, increasing the basis size on the numerically exact solution, which is all great. But they have, and actually we've got methods now with this multi-layer MCTDH that we can do, well, I'm not sure what the latest sort of record is, if you like, but Haobin Wang, who's a particular proponent of doing really large systems with sort of spin boson models, has done, I think, sort of 2,000 or 3,000 degrees of freedom in the propagation. Yeah? You can put the light field directly in the Hamiltonian. It's fully quantum, so whatever you want to put in, you just include it, right? Which is very nice. The disadvantage, though, is to say you need analytical potential functions because you have to know them before you start, and they have to be in a particular form, a so-called sum of products form. So that's its big drawback. So going to sort of slightly more approximate methods, but retaining the quantum character for the nuclei, are the sort of the family of methods that we call Gaussian Wavepacket methods, and I'll be talking about one of those later on. Yeah, so these are methods. There's families of them. So AIMS. It's multiple spawning from the Martinez group. There's the coherent states method of Dmitry Shalashilin. And there's the one I'll be talking about later, the multi-configurational Gaussian approach. No? And these are all methods where you expand the wave function in a set of Gaussian wave packets, Gaussian basis functions, and you propagate those rather than having a grid. So this gives you flexibility, and we can now do what are known as on-the-fly calculations, where we calculate the potentials as the propagation takes place, which is very nice. But they actually also are very expensive. Well, on the fly is expensive for other reasons because you have to do the quantum chemistry at the same time. But still, these still show a lot of promise for becoming more flexible and easier to use than the grid-based methods. And you can still, what I want to talk about today, you can include the light field just directly in the Hamiltonian if you want to. And then at the most approximate end of the sort of family of methods are the trajectory-based methods. So these are things like surface hopping, air and phase dynamics, Bohmian mechanics, or whatever. although Bowman mechanics is still fully quantum if you can actually solve it. But these sort of trajectory methods, you have the nuclei now have a classical basis to them. So you're losing the nuclear coherences. These are not variational, they're not complete, but they can actually give very useful information about sort of propagations, how a nuclear system propagates in time. They scale linearly, so they're much cheaper, but you can't, for example, put the effect of a light field in directly, and they're really not able to, I think, capture the real quantum behavior of a molecular system. Okay, so what is the MCTDH method? So just very briefly, in the MCTDH method, we have our wave function, which is just a function of the nuclear coordinates, and we expand this in a direct product basis of nuclear basis functions, which are termed single particle functions, or SPFs. Okay, so these are just time-dependent functions, and we've also got here, I'm summing over a set of electronic states, so you have an index for the electronic state you're on as well, and then you propagate these time-dependent functions and the time-dependent coefficients using this variational set of equations of motion. Okay, and you stop at the bottom of if you like, the tree. So we are expanding our wave function in terms of these wave packets, these single particle functions, and these are actually represented in terms of a grid, in terms of time-independent basis functions. So you have, this is where our sort of variational foundation lies, that allows you to really simulate the whole system quantum mechanically. Okay, and with this, so we can propagate really large wave functions, and then you have the problem, well, where do we get our potential energy surfaces from, or our potential functions, our Hamiltonian? Because as I said, you need analytical functions, and you are not going to fit accurately functions of more than a few degrees of freedom. It's just too expensive, takes too long. But for photo-excited systems, there's a rather nice model that we use really quite a lot, called the vibronic coupling model, that's able to take into account all the non-adiabatic effects of a system, at least over a short time scale. So what the vibronic coupling model is that we assume a so-called diabatic representation. So we have a diagonal kinetic energy operator, it's diagonal in the electronic states, and we have all the couplings between the electronic states in terms of diabatic functions. So we have diabatic potentials with diabatic couplings that are smooth functions, because we need to be in a diabatic representation for these simulations, because the adiabatic representation that you get directly out of quantum chemistry, the potential surfaces you get from quantum chemistry calculations, puts singularities into the kinetic energy operator where the surfaces become degenerate at so-called conical intersections. Yeah. So in this diabatic model, say we assume these nice smooth potentials, so we simply do a Taylor expansion of the matrix elements of these diabatic potentials, and that gives us our surfaces and our couplings. So we can fit these low-order polynomials to calculated data, we can refine it using experimental data and so on, so you can really get good descriptions of the surfaces and the couplings between the electronic states over a fairly limited region of the space around the Franck-Condon region where the excitation takes place. And one of the nice things about the vibronic coupling model as well is that you can use symmetry to say which are the important vibrations of the system. Yeah? So by looking at for example, this is our Taylor expansion for the couplings between the electronic states. So if we look at the linear terms, from the symmetry, you need to have the symmetry of the different states. So this is one state coupling to another state, and the symmetry of those two states, when you take the product of those and you take the product of the symmetry of the vibration coupling them, that has to be totally symmetric. Yeah? So only some of these terms are non-zero, and you can tell which vibrations couple the different states of the system. And I'll be coming back to that at the end of the talk as to one of its importances. Okay, so how well does this work? Well, this is an example I rather like, so I just wanted to show this one. This hasn't got anything to do with atochemistry, but it has got to do with sort of fundamental molecular dynamics. This was a study looking at this molecule cyclobutadiene. Cyclobutadiene, C4H4. It's a well-known, unstable, small, what's known as an anti-aromatic molecule. And it's anti-aromatic because it doesn't have enough electrons to fill the orbital. So you've got, these are the three main configurations involved in the ground state wave function. Yeah, we've got two electrons taking that are sitting in these pi orbitals. This would be for the situation if it is a square. Yeah, you think of a square planar molecule for C4H4. And because of this instability, you get a Jahn-Teller distortion, and the molecule actually isn't square. But because it's so unstable, it's actually very difficult to study. And until recently, there wasn't, for example, this was the best photoelectron spectrum that had been taken. And so even the ionization potential wasn't known with any great accuracy. And I got involved with this project because a group in Würzburg, Ingo Fischer, they hoped they'd measured the photoelectron spectrum of cyclobutadiene using a synchrotron, and it didn't match anything really in the literature. So they were somewhat worried about what they measured. So we got involved, set up a vibronic coupling model. So what you do is you calculate points, fit these surfaces. Yeah, so these are the diabatic surfaces going through the adiabatic points, or at least these are the adiabatic surfaces that come from the diabatic potentials fitted to the points that you get. Yeah. And we fitted at a relatively high level of theory, so CAS-PT2 level with a big basis set. And once you've got these surfaces, you can calculate the spectrum. Yeah, so this is just doing a direct excitation, sort of white light absorption. And you get the spectrum by calculating the autocorrelation function. So if you propagate a wave packet over these potential surfaces, you calculate the autocorrelation function, so the overlap of the wave function with its initial wave function. You take the Fourier transform, you get the spectrum. And this is our sort of scheme, if you like, for the sort of the surfaces. It's one of the things you look at, because the key vibration is this one here, and it's the one that if you follow where those arrows go, it's the one that takes the square through to a rectangle in both directions. So if you follow those two, you stretch in this direction, and if you go in the other direction, you stretch in this direction. So you're able to go from the rectangle this way to the rectangle that way in this coordinate. And these are the other two important vibrations that we found. Okay. So these are the sort of surfaces, the ground state of these three surfaces with these crossings. So it's a doubly degenerate surface in the diabatic picture with this other one, and this is the ion. And we're doing a vertical excitation from this well up into the ion state to calculate the ionization spectrum, the photoionization spectrum. And this is the comparison of the measured spectrum, it's the black, and this is our calculated. So this was with no adjustments of the potentials. That was just how they came out of the calculations, fitted to relatively high order, must be said. And the agreement is, it's really rather nice, and this allows us to look at the spectrum, analyze it, say which vibrations are involved, and to show, just what the frequencies of these peaks are that are underlying this band. So you can pull out from the spectrum the dynamics of the molecule, because these frequencies, these three bands rather, they are not just the fundamental frequencies, they're all strongly coupled due to the vibronic coupling between the states, and so these vibrations all mix to shift the frequencies significantly from their harmonic frequencies. Okay. So as an example of, again, the sort of thing we can do with these vibronic coupling models, but now including a light pulse, this is an example looking at a calculation of REMPI spectrum. So this is a multiphoton ionization spectrum, a resonance multiphoton ionization spectrum, in fact, of phenol. So 1 + 1 means you're just putting in 2 photons. These are actually photons of the same frequency. So it's a single color, but 2 photon excitation. And this was a set of experiments that were done by Joe Woodhouse and my colleague Helen Fielding here at UCL. And so they basically took these are the curves of phenol, looking at the OH dissociation. Yeah? So this is a classic sort of photochemistry molecule. You have the ground state, and then there are 2 important low-lying excited states. There's a bound state here, that's the so-called pi star excitation, where you excite just onto the ring of the pi ring. And then you've got a dissociative, what's called the pi sigma star state, which leads to dissociation, and these sort of cross. And these are the 2 ion states for the after ionization. And so Helen and Joe measured this with going up at various frequencies. Yeah, so they're basically going up with these 2 photons so that you're coming up above the pi sigma star state and going right up into the high levels of the ion. And these were the spectra they measured, for the 2 photon spectra. Okay, or at least this is the electron. It's the binding energy. So it's 2 photons minus the electron kinetic energy, and you sort of see the spectrum moving across. And so the question was, well, what are you actually seeing in this? What are these, you appear to have two peaks here, there's a shoulder here, and so on, yeah? And even what's this down here, because this wavelength is right down below, going in the right direction, right down below, they even start that the initial excitation is below that level. So that must be just a direct 1+1 ionization. Okay, so again, we set up a model. Now we have to include into our excitation, we have the two light pulses that we're going to include directly into the simulation. So we have to also include the free electron continuum to take into account the fact that the ion states have one less electron. Yeah? So we have the ground state, the excited state. So this is the first two excited states of phenol. And then we've got the states for the ions, yeah? So the cation states after ionization, and they have to include a continuum for the outgoing electron. Yeah? So we just add that in a sort of discretized form. We're not treating the outgoing electron fully, so there's no resonances or anything like that involved. It's purely we take into account the kinetic energy of the outgoing electrons. So we've got the light field, and our photoelectron spectrum then is the long time population of these continuum states, because those are the kinetic energy of the outgoing electron. And we then have to set up the vibrotic coupling model. So we do that so that, for example, this is the photoelectron spectrum, just standard phenol. So we have to set up our states for the cation, that they match the photoelectron spectrum for that rather nicely. And likewise for the neutral phenol. So this is the excitation to S1. Yeah, so that's experimental against our calculated. And then when you've done that, you can put all of these states together and run the simulation. So you just set it, you put in the light pulses with the appropriate frequencies, and you see what comes out. And while you can sort of see over here, this sort of set of rather busy sort of spectra has the experimental, they're the blue lines, and then our calculator one over the top in black. And so while they don't match perfectly, they've got the right sort of features happening as you go up in frequency. I mean, they don't match perfectly because it's a really very complicated system. So getting all of the frequencies absolutely correct, and we only had, I can't remember how many vibrations we actually included. It isn't all of them and so on. But in any case, you see that you have this narrow band down at the low frequency. And then as you go up, well, it shifts to the right. You get this peak forming over on the left, which is what you see. This is the particularly nice one that you're getting this split into two peaks as seen in the experiment. And you're even getting this sort of tail over here, although it's obviously not in quite the right place. This one fails totally, but that's because we don't actually include the higher lying states. This is actually almost certainly including the dissociation, and there's another state that we don't actually include. So it's no surprise that here we can't match at all. And if you look at the state populations, I'll come back to interpret the spectrum in a moment, what you see is these are the state populations. Yeah, so this is our light pulse coming in. Okay. And we see that at the low energy, indeed, it's a non-resonant excitation. We're below the excitation of BS1, so we don't actually excite it, just non-resonantly, follows the pulse up and down. And so that means this is just the direct 1+1 ionization. Then for these ones in the middle, you just get a nice signal where you do populate S1. Yeah? And that's actually this peak moving across, it turns out this is the 1+1 excitation. So this is really going to the S1 state and then ionizing subsequently. Whereas this piece down that stays over here, this little shoulder here at that point, that shoulder there, and going up to there, that's the direct 1+1 ionization. And then up here in this region, we're even getting some excitation to S2, and that's why the S2 state can also be seen being ionized. Okay? So we're explaining the spectra and give a molecular description as to what these different peaks mean. Okay. So as a sort of a final example of some grid-based calculations, this is an example. This is now really down at the Atto scale. This is a little simulation we did looking at propionic acid, and this is looking at something called charge migration. So charge migration is the phenomena that if you have a state, an ion state that is composed of two different characters, yeah, so it's not, often ionization, the electron comes pretty much out of a molecular orbital. It's a sort of a single hole, and that they're very stable. But you get, for example, as in propionic acid, these two here, so state 1 and state 3, are a mixture of the HOMO, making a hole in the HOMO orbital, and HOMO -2. Okay, so it's about As you can see, sort of 80% of one, 20% of the other, and the other states the other way around. And this means that if I make a hole just in one of these orbitals, then because of the electron correlation between the two, you end up having to, you end up with charge migration, so the electron moves from one orbital to the other. Okay? So for example, here in propiolic acid, there are these 4 low-lying ion states. That's the sort of bunch over here, the green, the blue, the red, and the yellow over here. And if you look at the sort of electron density, it's sort of going from one side to another. If you look at the coupling between this first and the third, so the red and the green, these are these 2 states here. Yeah, that's the same color coding. So if you made a hole at one end, it moves to the other. And we've sort of played around with this, looking at what happens, because often calculations on charge migration are done on a static framework of nuclei. You make a hole in one of the orbitals and you can watch the electron moving backwards and forwards between the orbitals. But what does the nuclear motion do? And the answer is the nuclear motion just damps that out really very quickly. So well, this is just doing a vertical excitation, creating a superposition between the 2 states. So this is the populations of the cation states 1 and 3 with different amounts given by their ionization propensity. And if you do that, you can see that because of the nuclear motion, the damping, so this is the correlation, the coherence times, the coherence defined by the overlap of the 2 electronic wave functions, effectively, the off-diagonal density matrix element, you see that the coherence dies away very, very quickly. The nuclear motion just kills that coherence, so that the charge migration stops. So what happens? Can we sort of extend it? So we were playing with this a bit, and if we put in a pulse, okay, this is just exciting the coherence with a pulse. So the pulse has to be narrow enough in time, so it's broad enough in energy that you can create the superposition. So that's what you see happening here. Yeah, so as the pulse turns on, we come down off the ground state and we go into the 2 excited states. And we again see pretty much the same as the vertical excitation, actually, but the coherence goes on. It's lasting until about 30 odd femtoseconds. And then we looked at sort of, can you increase that by having a pulse train? So you have 2 pulses and you have to time them correctly. But if you do, you can see with either 10 or certain gaps between them, you can actually get that this coherence can be made, it's given a kick in the right way, and then it will carry on out to, as you can see here, you know, if you get it before the decay is finished, you can get the coherence here lasting out to about 50 femtoseconds. So that was what we were doing in this example. And this is looking at the actual charge migration itself. So if we're looking at the sort of spin populations, then you can see this is making the hole in the 1 orbital on the CC bond, and the charge, so that charge is moving over to the CO, so it goes over to the carbonyl group, and then back again, and backwards and forwards, and it oscillates between the 2 until it eventually, as you say, after about 25 femtoseconds, it's gone. Okay, so that's sort of the charge migration. So that's all examples of using grid-based dynamics, and yeah, you know, sort of including pulses and sort of accuracy we can get with that. But to move to more flexible systems, as I said, you can actually use what are called Gaussian wave packet methods as well. So if we take, starting from our MCTDH wave function, and we just replace our grid-based functions by a set of Gaussian functions. So these are just Gaussian functions, they just have parameters and they're localized in space. So this has the advantage that you only have to propagate the parameters at the center of the Gaussians, which sounds very nice, yeah. But you introduce the problem that you now have to worry about the overlaps between them because you no longer have an orthonormal basis. They're definitely non-orthonormal, and this can lead to numerical problems due to the fact you can get overcomplete bases and nasty overlaps. You have to calculate the overlap matrix the whole time, invert it, and this can be a problem. Okay, so the nice thing, though, is that you can actually combine the grids and the Gaussians and try and use the best of both. So if you have a system that you're trying to simulate that's got a very, very quantum part that's coupled to effectively a set of harmonic oscillators, you can treat the quantum part using grids, and then you can move out to this part with the Gaussians. So you don't need many Gaussians to treat a sort of a harmonic classical bath, if you like. And you can even make the Gaussians really classical and follow classical trajectories. Because the Gaussians that we have, they don't follow classical trajectories, they're actually variationally coupled, as we'll say in a moment. Right? But this gives this sort of general framework for quantum, semi-classical, classical dynamics, all in the one sort of package. Okay? And they do then connect to trajectories. So these Gaussian basis functions, the Gaussian wave packets, Yeah, if you just write them, you can write them. This is the form of what's called a Gaussian wave packet, where we have a width, this A here, a center, the Q, and then a momentum at the center, P. And you can show that in this sort of GMCTDH method, these parameters, particularly if we keep what's called a frozen Gaussian wave packet, so the widths are kept frozen, the P and the Q, then they move. Well, if I write it in this form, it's a sort of bit of a coherent state type form, so Q plus IP. It has a classical part, so Q dot is basically P over M, yeah, the velocity, and P dot is minus the gradient of the potential, i.e. the force, yeah. So that's a classical bit, and then you have a coupled part, and this is the variational coupling that we have in GMCTDH that couples the Gaussians together. Okay, and this gives them a sort of a variational character that means that, in principle, they're optimal for the calculations you're doing. So if we have only Gaussian wave packets, yeah, so rather than having this GMCTDH with grids, Gaussians, and whatever, if we only have Gaussian wave packets, then we call this the variational multi-configurational Gaussian method. Yes, so basically we're writing our wave function now as a superposition of Gaussian functions. Okay? Again, we've got the electronic states here written explicitly. And the nice thing about this method is that, well, we can now do what's called, as I said at the beginning, direct dynamics. So we can actually calculate the potential surfaces on the fly using quantum chemistry. So we don't have to go to the effort of constructing multidimensional potential surfaces. And at the same time, we can allow these surfaces to be more realistic, because obviously the vibronic, the LVC model, the linear vibronic coupling models, and even the higher order versions, they can't really treat any long-range dynamics because you are fitting them around the Frank Condon point. So long-range dynamics is not included. So these are the properties that this method has. So it's fast convergence because they are variational, so they're optimal. And you can do direct dynamics. They're conceptually very nice, and you have these trajectories at the center of them, which you can use for analysis very nicely. It conserves energy by construction, as long as you are doing the integrals exactly, which we're not, it's true. And this is then the problems. They're numerically difficult and they're expensive. Okay, but moving aside from those, they do work really very well. So this is looking at something called the autocorrelation function that I mentioned for calculating a spectrum, just on a small 4D model. But this is to show how well these Gaussians behave. So this is an exact calculation using the Gaussians or the grid. So this is the full grid result. This is the full quantum dynamics for the autocorrelation function here on the left. Yeah. After the excitation to S2 is just the autocorrelation function of the wave function. And these are the state populations. And to get this, we had about 4,000 single particle functions. It's an MCTDH calculation. And the underlying primitive basis, so the underlying full product time independent base grid is 355,000 functions. And as we go up and we add more Gaussians, so this is with 20 on each state, and you can do 40, 60, or 50, 60, you can see that it converges really very quickly. So they're good functions when they work. And so doing that, we have this recipe for direct dynamics, which I'm not going to go into any detail because that's not what I want to be talking about today. But in principle, we can calculate energies, gradients, and Hessians, which is what we need to do the integrals. You can get these all directly from quantum chemistry. And we then store the results in a database. So we're unlike other people who there's a lot of people now doing direct dynamics, particularly with trajectory-based methods, but they calculate at each time step the energies and the gradients required. Rather than that, we are storing results in a database, the energies, gradients, and Hessians of points calculated, and then we do Shepherd interpolation through these points and only calculate new points when needed to build up our potential surfaces. So again, we have to work in a diabatic basis because we're doing our integrals not just at the center of the Gaussians, and to do that, I'm not going to say any more about that. We use something called diabatization by propagation. So we propagate the adiabatic diabatic transformation matrix, that's S, because we know the non-adiabatic couplings, and we can propagate those. So we get at least hopefully reasonable sets of diabatic states. Okay, and actually sort of Carla mentioned at the beginning, so I'm the main developer of what's called the Quantix package, and so all these methods are in this Quantix package. With this, you can do all sorts of quantum dynamics calculations using a range of methods from MCTDH, VMCG. You can do surface hopping as well, and so on. Yeah, and this is something, a part of what's called the Cosmos project, funded by the EPSRC, that's allowing us to develop this so that hopefully more people than just my group can use it. Okay, so as an example of how well the direct dynamics method works in this sort of VMCG type approach, this is just a study of methanol. I shouldn't say just a study, because the students of Leon who did this, they're quite expensive and take a lot of time. So you firstly have to go about looking at your electronic structure theory. And so you try different methods, you find which states are involved, you work out which methods are good. Yeah? And then you find that, well, it's very hard to find a method that's stable, cheap, good, and accurate over a range of geometries, because one of the problems with electronic structure is it's all been optimized around the equilibrium geometry, you know, around stable places, and we are moving to non-equilibrium regions of space where it's very difficult to get away from having to use multi-configurational methods like CAS-SCF, which can become expensive, and CAS-SCF is often not that accurate unless you get the right CAS space and it's a well-behaved molecule, and then you might have to go to RAS or CAS-BD2 or whatever. Okay, but anyway, once you've worked out your electronic structure theory level, you can in principle just run your dynamics. Okay, so these are sort of cuts through the surface that Leon calculated, just for example, for methanol along the OH or along the CO stretches, because one of the questions with methanol, it's an important molecule in our atmospheric chemistry, or actually in sort of in space as well, is with different photons, different energies, either the OH or the CO bond breaks. Okay? And so this is looking at those two, and you can actually see the channels here. So the OH, you excite to the first excited state, clearly the OH breaks. Yeah? Whereas if you excite to the first excited state of the CO, there's a bit of a barrier. In fact, it comes more from the second. Anyway, let's see what happens with the dynamics. So we run the dynamics, and these are the surfaces then that come out of the dynamics. They have similar forms to the ones I just showed. They're much bumpier. Well, that's because we're doing Shepherd interpolation and because quantum chemistry is not necessarily so great. But anyway, we have surfaces that have the right properties. They're in the right ordering. They're diabatic because they are crossing. Okay. And then we can pull out from that just directly things like the branching ratios for the different reactions. So this is exciting to S1. You can see that mostly is the OH breaking, as I said, but some CO. Yeah? Not surprising from the surfaces, but you get a branching ratio straight out. Or if you go to S2, well, now mostly it's the CO breaking. A little bit of H comes off, and you get some OH breaking, and so on. Yeah? So you can sort of, and then if you go to S3, to the higher energy, actually now the proton is trapped, and it's almost entirely the CO bond that breaks instead. Okay. So just to finish, just to move to a slightly different sort of approach, and again, sort of connect to the Atto chemistry theme, there's another method that we've been sort of trying to develop over the years. This is work particularly with Mike and Rob at Imperial, and this is something using what we call the quantum Ehrenfest method. And we're using this in particular, so Mike's particularly interested in what happens when you create superpositions of electronic states. Okay. So to get to this quantum Ehrenfest type method that we are using, you basically take the VMCG ansatz and you sum over the states. Okay, so rather than having that sum over the states with the index for the states going into the expansion coefficients, you pull that out, and that comes in to these time-dependent electronic basis functions. Yeah, so you have this time-independent basis, which is a superposition of the electronic states. And if we assume, and this is the problem, we have to assume that these electronic states are diabatic, because this is for people who know about the exact factorization method. This is basically like an exact factorization ansatz, and there you end up with a sort of a gauge coupling the two parts. Yeah, from the time-dependent basis has a gauge or a sort of a coupling to the nuclear, and the nuclei have a non-adiabatic coupling back from the moving electrons. And if we assume a diabatic basis in our formalism, you get rid of that sort of gauge interaction. So we sort of have this picture of these Gaussian wave packets moving over a potential given by these time-dependent electronic functions. Yeah? So these represent electronic wave packets and gives us a time-dependent Ehrenfest type potential that the Gaussians move over. Okay? And the nice thing in the pictorial about this is that our time-dependent Gaussian, time-dependent potentials because they're basically a contraction over the potentials from the states and the off-diagonal elements of the states, and if you think of these as being diabatic states, yeah, then this means that depending on how you excite the system, you change the forces on the nuclei, and then this gives a very direct pictorial representation of that. So the idea, it's a bit small here, I shall show something that's makes it clear in a moment. This is ethene, so if you ionize ethene, then depending on which states you ionize, you create a superposition. This is meant to represent creating a superposition of 50-50 in cationic states A and C, or alternatively a 20% position where you're getting 20% of each of these 5 ion states. If you do that, then you actually excite different vibrations, either these two or these two, because the gradients, you're now including gradients due to the non-adiabatic coupling between the states. Okay? And so this is the same thing in a bit more detail. So looking at the states you get, I mentioned this with respect to the linear vibronic coupling model, the vibrations that connect different states are given by their symmetries. Okay, so for example, the ground cation state, that's a B3U, looking at this pi star state, which is a B3G, this is coupled by the torsional vibration, okay, which has symmetry AU. And these two are coupled by this sort of antisymmetric CH stretch, etc. So by creating a superposition where I make holes in both of these, I'm going to excite that vibration. That's what this sort of symmetry argument says. And over here, these are the two symmetric vibrations in ethene that are also important for the dynamics, the CC stretch and the CH symmetric stretch. And indeed, that's what running the quantum manifest calculations showed, was that if we make a superposition of just the A and C, yeah, so the first and fourth cation states, a 50-50 mixture of that, so this is the population, so we're creating a 50-50 mixture in A and C, then you get this, well, in a way, not an awful lot happens, but the main vibration is NM10, which is the CH, oops, this one, the CH symmetric stretch, okay? And the torsion, which is the red line here, is completely flat. Whereas if I make this superposition in all 5 states, you end up with quite different initial forces on everything. And now, because I've now got holes in the, including the torsion, so the X and the A, well, I had that before, but that balances from symmetry, but you lose the symmetry and you're now getting, the torsion gets excited and you get a huge excitation of the CC stretch. Okay? This is just showing the state populations. So that was work by Thierry Tran. Okay? So to summarize, we're developing methods so that we can do computer simulations. And the idea is these help or can be used to interpret experimental data by providing the molecular picture behind some sort of complicated spectrum. And they also give us this nice picture of the phenomena going on. So, things like how the gradients change by creating a superposition of states rather than excitation to a single state. Okay. So we need to include non-adiabatic effects. We may need to include the pulse, if we really need to look at the shape and as to what the pulse is doing. So grid-based dynamics is great. It's actually in its way quite easy. It's very accurate, but it's unable to treat flexible systems easily, just due to the limitations of the requirement of the potential energy surface. So in contrast, we have these Gaussian wave packet methods, whether VMCG or quantum manifest or whatever. They are flexible, which is great. The system can really go where it wants to go. And if we're doing direct dynamics, it will calculate the surfaces as required, but they are numerically difficult and they're actually quite expensive. So we are at the moment putting a lot of effort into making them cheaper, more efficient and more effective, okay? Because direct dynamics is really promising, but it's expensive. And also at the moment, it's still limited by the electronic structure theory that you can do. Okay? So with that, I shall finish. That's just a picture of my group at the moment. And say the work was done by, so the cyclobutadiene was done by Barry Mant, and the phenol Diptesh Day, Marcus Taylor, propiolic acid, Diptesh Day, methanol was Leon Sigrant, who's here at the back, all the others that no longer in this picture, and the ethene cation work was done by Thierry Tran. And with that, I shall hand back to Carla.
So thank you so much. Are there questions, comments? You are welcome to put your questions and comments in the Q&A tab or to raise your hand. And if you are on YouTube, we are monitoring the live chat as well. So we're first going to do this on Zoom, and then we're going to move to you. So please raise your hand. I know it's Friday, but or write on the Q&A. Are there questions? Well, I mean, let me start then, because the chair is supposed to provide the entertainment. So, you mentioned at the beginning or in the middle of the talk that sometimes you mix several different approaches and that certain approaches are more beneficial if your system is more quantum and certain approaches are more beneficial if you have parts of the system which are more classical. Can you explain to us what you mean by more quantum and classical?
Okay, well, in sort of so this is this sort of idea. Yeah, so you can treat some of it as more quantum. I think in a lot of this thinking is really this traditional system bath type approach. If you have a system where everything is strongly coupled, and therefore quantum in the sense that the electrons and the nuclei are coupled. So if you have non-adiabatic coupling, often you can reduce it to there are three or four vibrations that are coupling the states. They're very quantum. Yeah, just because of the fact that they're the states along which you have a conical intersection or whatever it is, and that is best if you can treat that using a grid because they're the most efficient because they are variationally optimal. So you don't need many functions and they are very well behaved and you can propagate them well. Yeah? Then the ones that are, if you like, more classical, well, they're the harmonic bath modes, as you'll call them, because these things can be treated very simply by, a single Gaussian wave packet is exact for a single harmonic oscillator. So they're very good for that. You don't need many functions to describe a lot of those sorts of dynamics. So that's the sort of thinking there. Yeah? And you can sort of see that if you look at a linear vibronic coupling model, where I had my Hamiltonian, in the sense that if I have something like a Hamiltonian that I'm expanding for the different, these modes that are involved in these linear terms, they're very quantum because they are coupling the electrons with the nuclei. Whereas if they don't come into the potentials, if you like, until lower orders, the coupling's weaker, you can treat them easier, they're more classical.
Okay. I think it's clear. It's just classical and quantum means different things for different people.
Yes. Yes.
It's always important to clarify. Hi, Andrew. Andrew Brown is here.
Oh, hi, Andrew.
Like to ask a question.
Hello, can you hear me okay?
Yeah.
All fine.
Just wondering about when you put these molecules in the strong fields or fields of any kind, what are the sort of limitations in terms of the regimes that you can describe, sort of laser wavelengths and intensities and so on?
Cool. I mean, in principle, it's only limited by the sort of the nature of the Hamiltonian. Yeah? I mean, you can do strong field ionization. Well, if things start to ionize, Andrew, you know more about ionization and electron dynamics than I do. And if you're trying to calculate something like the dipole surfaces that you would need to do accurate calculations with higher strength pulses, then the quantum chemistry breaks down at some point and you can't go any further. Yeah. But for strengths, for frequencies, I mean, again, you can't go to really very high frequencies because the integrators start to struggle. If you go to real, high, I guess, right up in the X-ray, because you're not going to be able to follow the pulse particularly well. So we have tended to stay, but we have no real problems in UV frequencies and relatively strong pulses. We've done things with sort of near ionizing pulses. Of course, if you have a model where you have a simple linear dipole, then you can go to any strength and nonsense will happen at some point. And then you will just see.
Yeah. Thanks so much, and thanks for the talk.
Thanks, Andrew.
Okay, I'm muted. We have another question also from Meenakshi Rana. Hello, Prof. My question is, can you please explain about edging electron continuum in MCTDH a bit? My second question is, they have two questions. One is this one, and the second question is about charge migration. It mean by electron correlation or resonance by induced dipole? How can there be only one reason of charge migration in a system?
Okay. Yeah. So yes, nice question. Yeah, thanks for Menassi. Yeah. Okay. So how we add the electron continuum? It's a very sort of simple model. So you have, instead of a bound state, you have a cation state. So you've got, for example, phenol. Yeah, very straightforward. You just calculate the potentials for phenol, but then you've got the phenol plus with the electron. So we have to consider what's happened to our electron. And all we actually do to it is we balance the, it's an energy balancing. So what we are saying here is I've got my cation state, which gives me a potential surface. Yeah, and I've effectively got one potential surface for each possible electron energy for the outgoing electron. Okay, so as I said, we're not considering the actual coupling between, the electron with the short time dynamics as it leaves. And so what we then do is this electron effectively gets treated as an extra degree of freedom, and it just is given a grid. And you just have a grid of energy so that we can discretize that kinetic energy of that outgoing electron on this grid. And this is just balances the energy of the Hamiltonian. Okay, so I hope that sort of makes sense. So you've got that, yeah, basically it's sort of difficult to see, but yeah, you just add it on here this is, so I've got the nuclear degrees of freedom for my wave function, and then I've also got the outgoing electron kinetic energy, just as a sort of another part to the wave function. Okay? And for your question about charge migration, good question. I'm sure there would be different ones. Yeah, you've got the induced dipole, so that's more when you've got the that would be more about the induced dipole between molecules. I mean, these are all whatever, people have names for things because they like to define different phenomena. And this form of charge migration is just one that's been used in a number of systems where you get charge migration due to the electron correlation, between the zero order states in the full eigenfunction. Yes, you can get charge migration from other things. So as you say, I think induced dipole, so just things like you'll get, charge migration between parts of a long system, or even between different molecules, things like first resonance and so on, that will give you charge migration. Yeah. The only difference in a way is that the categorization for me is that charge migration is something the electron's moving because of some reason, coupling between parts of the Hamiltonian, whether the electron Hamiltonian, that is, whether it's due to the induced dipole or, you say, resonance or electron correlation. That's just a different mechanism, but it's not due to the motion of the nuclei. Yeah, because some things, when you have charge transfer, the electron is moving because the nuclei take it to some other point on the potential surface. That's the distinction.
Sorry, is that clear to you? Yes, go ahead.
Yes.
You can ask. So I don't know how good your connection is, but if you would like to follow up, is it fine? Yes, we are hearing you.
Yeah, I got it. Thank you so much, Professor.
Okay. Yes. You're muted now, Carla.
Yeah, I mean, there was some echo, so I muted myself, but yes.
Okay.
So all good?
Yes.
Yes. So we have also a question from Yushen Wang. Thank you for the great talk. Can you explain a bit the relationship and differences between the quantum Ehrenfest you showed and the multi-configuration Ehrenfest of Schilling?
Okay. Yeah, so they are similar, and there are, but on the other hand, they are somewhat different. Yeah. So Dimitri's version differs from ours in the sense that, where is it? I've lost it here. So for a start, his Gaussians move on classical trajectories, whereas ours are on these variational trajectories. And as a result of that, he actually doesn't have the coupling between the parts of the surface. So the whole problem with Ehrenfest is partly how you define the surfaces that come from this time-dependent electronic part of the wave function. because you actually can't define it rigorously. So you have to make some sort of approximations. Yeah? And R's are defined by, these are defined at the center of the Gaussians. And we have this diabatic basis. Dimitri, his likewise follow the Gaussians, but they follow classical trajectories, as I say. So that's the main difference. He also has a slightly different way as to how he calculates his integrals. Yeah? We're doing this local harmonic approximation, and Dimitri, I forget what he does, but he's doing a sort of it's an averaged potential for each Gaussian. But other than that, actually, the mechanics, the rest of it, the ansatz, they actually look quite similar. So those are the main differences, though.
Is that clear? You can follow up as well if you would like.
Thank you very much. Yes, thank you.
Okay, you're welcome.
Okay, are there further questions? Let me have a look at YouTube because we have some people watching there, quite a few actually. Let me see if our subscribers have questions. I don't see anything on the live chat, but if you're watching right now, you can post your question and I'm gonna make sure that Graham replies. We are going to ask. I don't see anyone joining the conversation, but do feel free to do that. No, they're quiet on YouTube, although there are quite a few people. We have 15 on YouTube, so it's quite a lot. So feel free to reach out to us on the live chat.
I have a question, if that's
Go
all
ahead,
right.
please. Absolutely. Yes.
When you do calculations for specific molecules, does the chirality of the molecule change any of your like answers that you or graphs that you get?
Well, good question. I mean, the chirality, I mean, I guess you would only see difference in chirality if you're including a light field, because obviously chirality doesn't play a role in a potential surface. So if you're just doing our standard, I've got a potential surface, do a vertical excitation for my wave packet, and off it goes, chirality will not show any differences, yeah? Because it doesn't matter which way around. It doesn't know that part. But of course, if you put in a light field, then it would. Yes, if you have polarized light and so on, then that would interact differently with the different chiralities of the molecules. Just the sort of, we've never tried that. I mean, putting in a polarized light field, be interesting actually. I wouldn't exactly know an easy way of doing that. But if you can write down a Hamiltonian for a polarized light field and how that would interact with your coordinates, then yeah, you would have to, it should show a difference. It would be a good challenge. I mean, because it's well known that obviously polarized light, different chiral molecules, it changes the polarization, and therefore it's going to also affect the dynamics somehow. Yeah? So the answer is we've never seen it because we've never looked, but it might or should.
Thank you.
Okay. A problem for the weekend, and sort of go and see if we can do it.
So let me check YouTube again. If there's anyone reaching out. No, I cannot see any question. So we will have the opportunity, if you would like to reach out to Professor Worth more in private instead of having your discussion broadcast over to the internet. But I mean, I think by now, after all these years, we are all used to that anyway. But you have the opportunity because we're going to end the streaming. So for those watching on YouTube, thank you so much for supporting us. Take good care of yourselves. Have a great weekend. And next week, we're going to have Vincent Vanni talking about something related to free electron lasers. We don't know exactly what, but take care and thank you so much for watching. See you soon.